In these videos, we're going to look at an introduction to some of the basic ideas and formulas and methods about Laplace transform methods for differential equations. I'm not sure I figured out the best way to introduce this topic in my book. I think maybe the best way is just to dive in. So that's the approach we're going to take here. We're going to start off with the definition of Laplace transforms, which is in this box. Is kind of a funny looking definition if you've never seen anything like that before. So we're going to do an example right away to try to begin getting a feeling for how this definition works. I do assign a lot of problems for my students in my DE course where they have to calculate various things using this definition. I feel like it's pretty fundamental. So we're going to, the main goal here initially is just to start getting comfortable with this definition. So for our first example, we're going to take the Laplace, the function of time defined by e to the at. Based on our previous work in differential equations, we know that exponential functions play a very important role in a lot of differential equations, so this should seem like a good place to start, and we want to figure out what the Laplace transform of that function would be. So here we go. To start off, we just take that function formula for f of t and plug it into the definition. That's the first thing that's happening here. Then we can use a little elementary property of integrals to combine the two exponentials under the integral, and that's what's happening there. There are, of course, other ways to write that exponent, but because of the goal, the formula that we're headed for, I will choose to keep it in that form. Now we're going to look at the antiderivative here first, then we'll go back and calculate the definite integral once we have our antiderivative. So for the antiderivative, I'm going to go ahead and go through this in some detail. We use integration by substitution where u is minus s minus a. T, remember t is our integration variable, so du is minus s minus a dt, which I then solve for dt here. Then I took my integral here and got everything in terms of u, so that gives me e to the u and the expression which I just found for dt. Now here s minus a is constant as far as t is concerned, or as far as u is concerned, it's a constant. So I pulled out minus 1 over s minus a. Then I just have this integral, which we can do immediately and get this, and then we go back to write that as a function of time, which is our original goal. So that's the antiderivative that we need in order to calculate the indefinite integral. Or sorry, the definite integral, this definite integral here, which happens to be improper. So I'm going to go through this one a little bit carefully. I'm going to start sweeping some of the details of the theory under the rug in some of the later examples, but I'll go ahead and do this one carefully so we can see what's going on. Whenever we're dealing with an improper integral, there's some kind of limiting process going on, so the definition of that improper integral is basically what's going on here. It's defined to be the limit as b approaches infinity of this definite integral. In the next step, I just took the antiderivative, which we found up above, and plugged in, and I'm just using the fundamental theorem there. And so now I'm just going to evaluate that expression which is going to turn out to be a function of b, and I'll take the limit as b approaches a when we're done with that. Now the first little baby step that I did with this is we're going to end up having a lot of minus signs in a lot of these calculations, and I like to get rid of minus signs right away when they pop up. So I just use the minus signs in the next step to flip the limits of integration here. So that made one of the minus signs at least go away. Now I'm just plugging in here. In the next step, I'm plugging in 0 for t. For the upper limit, that gives me e to the 0, which is 1. And plugging in b for t in the second term. So now we have our expression in terms of b. We're thinking of s and a. We're thinking of as being constants throughout this whole calculation. And now on the next slide, we're going to take the limit of that expression as b approaches infinity and see what we get. As a friendly reminder, for these videos in particular on the Laplace transform methods, I believe it will be very helpful if the student will try to take some notes as we're working through things together, especially anything that's in a box. For example, this formula here, the definition of Laplace transforms, that's something that the student will probably find it helpful to record that in their notes. Now, I do not expect my students in my DE course to have all of this information memorized. In fact, I give them a table of Laplace transforms early on in the chapter, and I encourage them to use the table as often as they need it. There's something like 20 or so total formulas in my little Laplace transform table, which is plenty for anything we ever have to deal with in my course. So it's not about memorizing these formulas, but I do want students to get comfortable with them and understand some of these relationships. And certainly I expect folks to be comfortable with the definition of Laplace transforms Formula 1 on this slide. In practice, what usually happens is after my students have been working with Laplace transforms for a while, they can certainly remember some of the most commonly occurring ones, but I always let them use the table if they need it as a backup on homework, quizzes, and tests. So back to our calculation here, we're not quite done yet with this problem. We have our function e to the at. We're looking for the Laplace transform of that function, and we got it down to here. So we'll pick it up there, right there, and finish that calculation up on the next slide. So this is a problem we're trying to solve to find the Laplace transform of e to the at. At the bottom of the previous slide, we had this expression, and now we're ready to take this limit as b approaches infinity. Now we want this thing to converge, and in order for that to converge, we can assume that s minus a is just some positive number, or equivalently that s is greater than a, in order to have that limit exist and be finite. So if b is approaching infinity and s minus a is any positive number, then the limit of that term is just going to be 0. And so we end up with 1 over s minus a for our Laplace transform. So we proved using the definition that the Laplace transform of e to the at is the function 1 over s minus a. In general, in this chapter, we're going to be starting out with functions of time. Typically, those are going to represent the solutions of the differential equations that we're trying to solve. And the Laplace transform of a function of time is always going to be a function of s, which we can see here. That's pretty typical notation that people use in connection with this topic. There are occasionally you might run into some slightly different notation, but that notation is fairly typical in connection with this topic. For another example, here we're going to look at the function f of t as 1 and try to figure out the Laplace transform of that. The first way we're going to do that is we're just going to plug in a equals 0 up here, then this becomes 1. So we immediately then get the Laplace transform of 1 is 1 over s. So that's the fastest way to get our answer. Laplace transform of 1 is 1 over s just by plugging into formula 2. I also want to show you how to do that using the definition so we can get hopefully a little more comfortable working with the definition, and we should get the same answer as we did using solution method number 1. So if we just take that function f of t equals 1 and plug it into our definition of Laplace transforms, the Laplace transform of 1 must be that integral. And I'm going to take a few shortcuts here now and kind of handle this the way a lot of engineers and physicists would do it. There's really still a limiting process going on, but I'm going to sort of sweep that under the rug a little bit here as a little bit of a shortcut to get the answer that we're looking for. So here I just anti-differentiated, found my antiderivative with respect to t, plug in infinity, plug in 0. Here I just use the minus sign to flip the limits of integration so I don't have too many minus signs hanging around. So I'm just using the fundamental theorem now, and roughly speaking, that's my answer. There's really a limiting process going on here, so there's a little bit of a shortcut there in the way I'm writing it. And if we assume s is some positive number, in order for this to converge and have a finite value, then that will make this term drop out. And the limit as we go to plus infinity, if s is any positive number, that exponential approaches 0. And all we're left with is 1 over s, which agrees with what we got before up here using solution method number 1. So at this point we have 3 basic Laplace transform formulas, which hopefully, as a minimum, hopefully those 3 are recorded in your notes if you're watching this series of videos. Formula number 1 was the definition of Laplace transforms. Formula number 2 in the red box up above is the Laplace transform of e to the at. Formula number 3 is the Laplace transform of 1, turned out to be 1 over s. And those are going to be basic ingredients in everything else that happens later in this section and in this chapter.